Uh, Good morning, Ignacio. Thank you
Morning.
for, yeah, really appreciate your making time for us. I'll just, I guess we're pretty much on time actually. We usually start a few minutes later than the announced time. So what I'll do is, can you just please check your screen that you can share properly?
Yeah, let me check that.
Oh, that's great.
That
I'll
works.
just make
Okay.
a brief introduction and then we can start. So Ignacio is a research scientist at Google Research. His research focuses on the development of data-driven weather forecasting systems with an emphasis on extreme events and on climate modeling and analysis. He holds his PhD in environmental science engineering from Caltech, and I presume your advisor was Tapio Schneider.
That's right. Yeah.
Yeah, no, Tapio is a great mentor to our center, so it's good to have you have that connection as well. So he developed a model of atmospheric turbulence, convection, and clouds for climate models, which are, of course, extremely essential to build accuracy. Very happy to have you here, Ignacio. Look forward to your talk.
Yeah. Thank you. Thank you for the introduction, and thanks everyone for bearing with me. I know it's late in India. And so today I'll be talking about some of our recent work at Google Research on downscaling, that is increasing the resolution of climate projection ensembles using generative AI. And here, the end goal of our work is to improve the state of the art in regional climate risk assessment, both for present climate and for future climate. So the main reason why we're interested in this problem, in downscaling, is because global climate projections, as they stand right now, are too coarse to capture many important physical processes that affect local climate. Some of these processes are orographic effects, so the effects of topography, mountains, and so forth, convective precipitation, and also the onset and evolution of some emergent phenomena such as tropical cyclones. These are not resolved by current climate models. And so this is a problem because if we want to actually assess certain risks, certain climate risks, we actually need higher resolution than this. And to put this into perspective here, I'm showing on the right-hand side of the slide a spatial distribution of the rainfall totals during the November 2000 floods that occurred in the Big Island of Hawaii. So we can see that there was a very strong spatial gradient in the distribution of rainfall totals, with most of the rain actually falling on the eastern side of the island where the capital Hilo is. And what's important to note here is that actually the entire Big Island of Hawaii fits in a single grid cell of most of the climate models in the CMIP ensemble right now. And so if inhabitants of Hilo were to use just data from climate models directly to assess risk, you can imagine that it's not going to be a very useful estimate of risk in these situations. So high resolution is one of the pieces that we need if we want to truly advance the state of the art in regional climate risk assessment. But the other piece that we need is access to long climate records. For instance, if we're interested in understanding what the magnitude is of a 100-year precipitation event, right? Like a precipitation event that is so strong that it only happens every 100 years or so, we will need a few hundreds of years of data at least to estimate this robustly. This is an issue that is compounded due to the fact that we live in a changing climate, which means that even if we had access to, say, the last 2,000 years of climate data, because climate is changing, historical data is not necessarily a robust predictor of present or future risk. And so in this situation, what we actually need in order to assess climate risk are ensembles of climate projections for the present and into the future. And the issue is that physics-based models are too computationally expensive to actually get this to these two tasks that we need. Because of this, we're going to need to assess if we can use other strategies to obtain regional climate information. So one of the methods that we can obtain for and that we can use to obtain local climate information is the so-called dynamical downscaling approach. This is a method that uses regional climate models, which are essentially climate models that just trade spatial extent for spatial resolution. So as an example, the domain that you see here on the bottom right of the slide. And these models are forced by both the boundary conditions and large-scale conditions of a climate model, an Earth system model. And because of this, because they use the equations of motion and the physics understanding that we have of climate, they're very robust to climate change. So we think that to the best of our ability, these models actually capture physical processes that happen at warmer temperatures with a changing climate. So that makes them attractive. An issue with these methods is that they remain too expensive to downscale large ensembles and capture uncertainty. So as I was saying before, these models trade spatial extent for spatial resolution, but they remain roughly as computationally expensive as just running the climate projections that we needed in the first place. And so we cannot apply this to the hundreds of ensembles that we would need for climate risk assessment. And so we need more efficient ways of obtaining this information. So cheaper methods in order to obtain localized climate information do exist, and these are usually grouped into the statistical downscaling methods as a group. These methods are typically designed to preserve the trends in the input Earth system model, and then statistically add details, add fine-scale details based on the historical data that we may have access to from weather stations, from reanalysis products, and so forth. So these methods are drastically cheaper than dynamical downscaling. However, they come with some limitations that are related to some of the assumptions that these methods make in order to make their predictions. So I'm just going to give two examples of these limitations today. So one of the main limitations of these methods comes from the stationarity assumption, which they make, which essentially means that these methods are going to assume that the fine-scale details that we're going to add to the Earth system models are basically constant with climate. And these are just given by the changes that you would observe in the historical record. And because of this, these methods are going to miss some important physics in some regions of the world. An example of this physics is, for instance, the lack of snow albedo feedback in statistical downscaling. So snow albedo feedback is essentially the observed and predicted faster warming that occurs with climate change in regions in regions at altitudes that are close to the snow line. So if you imagine a mountain range in the areas where there's some snow accumulation during the year, as climate warms, that snow is going to melt, albedo is going to change, and those regions are going to change even faster than other regions. And so here I'm showing an example for the Sierra Nevada mountains in California, where we try to predict the temperature change in early spring with an Earth system model. We get a smooth field just because of the fact that these mountains are not resolved at the scale of many climate models. However, if we use a regional climate model with high resolution, we can actually start to see the warming trends, the more localized warming trends in the mountain range, as shown here in the second panel, in the center panel in the slide. The problem is, as I was saying before, that if we use statistical downscaling methods, such as the popular BCSD method, we essentially just preserve the trends of the incoming of the input Earth system model, and we're going to fail to predict these changes, which can be very important for regional risk in these situations. Another limitation of traditional statistical downscaling methods is that they typically, because they use simple statistical models, they typically tackle one variable at a time. So they perform univariate modeling of climate fields. And this can lead to issues, and in particular, one important problem of this approach is the underestimation of compound extremes. And so As an example here I'm showing the just the wind speed magnitude. So if we consider the wind speed magnitude, this is typically composed of, if we think about the horizontal speed of two components in the zonal and meridional direction. And so if we have a method that is going to just neglect completely the correlations between these two fields, and then we say try to estimate the magnitude of extreme events, we're going to severely underestimate the magnitude of the events where there's a positive correlation between the two components. And so here, as an example, I'm showing the top percentile of fall wind speeds over the Western US, computed with a regional climate model in the middle of the slide, and with a statistical downscaling model to the right. And you can see that the statistical downscaling method systematically underestimates the magnitude of the top percentiles of the wind. And so in this context, what we wanted to understand, or we wanted to work on, is whether generative AI can help solve this problem. And so we have this schematic, this picture where we have two approaches, where we have a fairly cheap approach, statistical downscaling, that fails somewhat in the scale and that of the forecast that it provides in terms of the added value that it provides to downstream users. And an approach, so running regional climate models or dynamical downscaling, that has provides a lot of added value, but it remains still too expensive to apply to climate ensemble projections, which is necessary for climate risk assessment. So the idea here is whether we can use generative AI to essentially roughly retain the skill of regional climate models, but do so at a much reduced cost, such that we can actually apply these techniques to large ensembles and then estimate robustly the risk of extremes. And so we've been working on this problem for about a year and a half or so here at Google, and we've developed two approaches that work quite well and use generative AI to accelerate the downscaling process. And so these two downscaling techniques are developed with slightly different applications in mind. And so the first approach that we've developed is what we call dynamical generative downscaling. So it's a mixture of dynamical downscaling and generative AI. And this technique is particularly developed or designed in order to enable downscaling ensembles of multiple climate models. So if we want to, for instance, understand, in many situations, we want to understand the uncertainty that comes from just the different models that we're using, because models have errors, and these errors are different. And so, for instance, if we want to understand, say, what the daily maximum temperature in Montreal is going to be at the end of the century, we typically see that for questions such as this, model uncertainty is actually driving the total uncertainty. And so here I'm showing that on the top right panel in the slide, where model uncertainty is the blue shaded area. So you can see that it covers roughly 80% of all the uncertainty. So it's important to capture. But there are also other applications where capturing model uncertainty may not be that necessary, where most of the uncertainty is actually related to internal variability, just to the chaotic nature of climate. And so for this application, we can go a step further and just use generative AI for downscaling, which enables us to drive the cost of the downscaling process even further down. And so for this, we've developed a second approach that is particularly designed for single model ensembles. And so applications of this could be, for instance, the estimation of risk of precipitation in many regions of the world, which typically, even with climate change, is still largely driven by internal variability, not everywhere, but in many areas. Or if we're just interested in more immediate climate change, so let's say climate risks in near-term horizons of like 5 or 10 years, then internal variability is usually the major driver. And so I'll be showing some results for these two approaches today. So the first approach that I mentioned, as I said, is what we call dynamical generative downscaling. And it's called like this because it has essentially two components. the first component is going to use, similarly to dynamical downscaling, a regional climate model. But in this case, we're just going to use the regional climate model to downscale the projections to an intermediate but still cheap resolution. So the objective of this step is not necessarily to really increase the resolution very strongly, but it's to essentially promote generalization of the method across different forcing Earth system models. And I'll touch on this a bit more on the next slide. And then after using this first component, we're going to take the output of the regional climate model, and we're going to use here a generative model to downscale this data even further to the actual target resolution. And this is the step that is going to enable us to really save in computation, and it's going to enable efficient sampling of high resolution climate data, which is important to apply to large ensembles. So going a bit more into the different stages of the method, as I said before, in the first step, we're going to use a regional climate model for generalization. And the reason why we designed the method this way, the reason why we need this step, if you want to generalize across multiple climate models, becomes a bit more clear when we try to delve in and actually consider what different climate models look like. And so here on the slide, I'm showing on the left-hand side a table of different models within the CMIP6 ensemble. So from the same sort of stage of the CMIP effort. And we can see that even though these models are roughly developed at the same time, they have very different resolutions. So there's models that have almost 3-degree resolution, and other models that are closer to 0.7, 0.9. And so if we think about just training a machine learning model on data from one of these climate models, say from Access CM2, the first model, and then we use that model on any of the other climate models, it's easy to understand that there's going to be a very, very strong generalization gap, just because the inputs that we're using for training are very different from the inputs that we would be using for inference. And so this can be understood also in terms of the spectra of different fields. And so here I'm showing an example in the middle of the slide where the different colors are supposed to represent different climate models, but with the same variable and the same diagnostic. And we can see that for different climate models, if they have different resolution, the spectra or the energy at every scale is going to be very different. And so in this context, what using a regional climate model allows us to do is to really align those spectra, define scales, and form a stable basis for generative model or for machine learning more generally in our method. And so what this is going to allow us to do is essentially to generalize to multiple climate models, which is the goal of the method. So once we've developed this first stage, once we've mapped everything into the same resolution of a regional climate model, then we could use generative AI to get to the highest resolution. And so the way that we trained our generative models here are, because we assume we have access to a regional climate model for the first stage, we just generate further training data to the higher resolution with maybe just one climate model. And then we learn an emulator that gets you from the intermediate resolution to the highest resolution using generative AI. And this model then is going to enable us to add the missing fine scale processes and capture the internal variability at the small scale. So for this, for our work in particular, the generative model that we've used for the second stage is a multivariate diffusion model that we've called R2D2. So this diffusion model essentially takes as inputs different climate fields at some coarse resolution. And then it's able to add fine scale details to these fields and probabilistically estimate the high resolution climate of all of these fields together in the output. And so importantly, these diffusion models are very effective at capturing both spatial correlations within the fields, as well as variable correlations. So for instance, here I'm showing examples for wind speed, for zonal wind speed, and for temperature. And so the samples that we get when using these models, when we assess, for instance, the risk of compound extremes, because we are capturing the correlations between the fields, are not going to lead to the underestimation problem that typically statistical downscaling methods have. And so another useful property of these methods is that because they are probabilistic, we can actually use them to capture the internal variability of the fine scale condition on the large scale conditions in the input. And this is going to be useful to assess more robustly the probability of, say, low likelihood but high impact extremes. So we've applied this methodology to climate projections over the Western United States. And the setup that we use for this project is shown in the schematic here on the slide. So the inputs that we used were CMIP6 models, so a few CMIP6 models for evaluation. They're all taken with the SSP3 forcing scenario. So we just chose one scenario for this particular study. And in terms of the methodology, the regional climate model that we used for the initial downscaling stage is the WRF model, so the weather research and forecasting model. We use this method to downscale data to a 45 kilometer resolution, which is still fairly coarse over the domain that you see on the slide, in the middle of the slide. And then finally, we used R2D2 to downscale this data much further, all the way to 9 kilometer resolution. And so for our particular study, we did this for 6 different fields, capturing precipitation, winds, temperature, and so forth. Now, because we're interested in climate model generalization, the setup that we used in our study was to train R2D2 on a single projection from a single climate model. In this case, we trained R2D2 on climate projections from the Canadian model CANDI-SM5. And then to assess generalization to different climate models, we evaluated our model on an ensemble of 8 Earth system models, which were not seen during training of our method. And so here, because we're using a setup where the ground truth is still dynamical downscaling, is where you're going to use as ground truth for validation data from WRF. So the results that we obtain from using this methodology show us that the downscale samples from our methodology are very realistic. And so some of the properties that we observe is that, for instance, dynamical generative downscaling captures very well the fine scale spatial structures of the flow. And so here on the left-hand side of the slide, I'm showing the energy spectra of 10-meter winds over the continental United States, computed with our method in green, from the target in black, which is essentially just superimposed with our results, and the results that you would obtain from other statistical downscaling baselines that are popular, such as BCSD and STRUSDM. And so we can see that our approach captures essentially the energy correctly at all scales, where their statistical downscaling methods typically fail to capture the entire range of energy at the smallest scales. We also looked at the covariation or correlation between different climate fields, and so here on the middle panel of the slide, I'm showing the covariance structure between zonal and meridional winds at the Shepherd's Flat wind farm in Oregon, which is one of the largest wind farms in the United States. And so here the target or the ground truth is shown as field contours in blue, and the covariance structure that we obtain using our method is shown as green contours, which you can see are essentially again superimposed on the ground truth. So we capture really well the structure of the flow, whereas results for the other methods typically yield a wider structure in the correlation, which is essentially telling us that it's really not capturing the correlations very well. It's more of an uncorrelated simulation of the two components of the wind. We've also looked at how well the model is able to capture not only correlation between components, but also covariation of extremes in different components. And so for this, we looked at the tail dependence of zonal and meridional wind and other components as well in the paper. And so here we see that essentially on the two maps you see on the right hand side of the slide, R2D2 is able to really recover the covariation of extremes similarly to dynamical downscaling. So um, so at least the samples that we obtained from our method look extremely similar to those from dynamical downscaling. So we also looked, of course, at more formal analysis of the scale of the method. And so in downscaling and bias correction, more generally, something that is important to assess is whether we're actually reducing the bias at the high resolution with our methods. And so for that here, we looked at the mean bias for downscale projections from our approach at the end of the century for temperature here in panels A and M. And so the results that we obtained with our method R2D2 are shown in panel M, where we can see that the bias is fairly weak. It's about 0.16 degrees Kelvin over the Western US. And this is smaller than the bias that you would obtain from, say, statistical downscaling method BCSD, which is still, I mean, statistical downscaling methods have some limitations, but this is one of the particular applications where they shine well. Because they're based on essentially quantile mapping approaches, and they're particularly designed to minimize bias. So the fact that we can actually improve upon these techniques in terms of bias is really good news. Of course, bias just tells us about like whether there are systematic errors in our prediction. It doesn't tell us what the typical error is when we make predictions of fine scale on fine scale weather. And so, in order to evaluate this second metric, we looked at the CRPS, which is a measure of essentially probabilistic error when comparing sample to sample or date to date. And I'm showing here results for temperature and precipitation on the second and third columns in the slide. And so we can see here that R2D2, our method, which is shown in the bottom row, really shines bright compared to statistical downscaling. It reduces the errors that we observe when downscaling by more than 40% for temperature, precipitation, and other fields. And so here we see significant improvements above, beyond what's available with statistical downscaling. Another useful property of diffusion models and our approach is that being probabilistic, we can actually sample many times different high resolution fields for a given input. And this enables us to essentially estimate whether our method is able to robustly capture the uncertainty in the process. And so we do this in terms of the so-called spread skill ratio, which just tells us whether the spread in our ensemble predictions is fully capturing the error that we typically observe in the predictions. And so I'm showing that here on the bottom right of the slide for precipitation, and we can see that our method robustly predicts most of the error over the continental US for these predictions, which is going to enable us to make more robust uncertainty statements. And so, of course, this is only available. This is only something we can do with probabilistic methods. And so, for many of the classical statistical downscaling methods, such as BCSD, we actually do not have access to this sampling ability. So we don't actually have access to these estimates.
I had a,
Yeah.
yeah, so the R2D2 that has been trained, what is like the ground truth data? Like when you have diffusion, you have some samples that you're like, what is the ground truth 9 kilometer data that's being used here?
Yeah, so we used so we've trained R2D2 as an emulator of a regional climate model. And so in this case, what we did is we used dynamically downscale data from WRF all the way to 9 kilometers for just one of the climate models from the ensemble. So we used the Canadian model to force WRF to 9 kilometer resolution. We trained our model on this data, and then this enables us to then downscale the rest of the ensemble, the rest of the climate models in the ensemble.
So just to be sure, given any sample from any climate model, you first apply this first model to go to 45 kilometer scale. And this R2D2 then will take this from 45 to 9, regardless of what the first model with the coarse projections was.
That's right. Yeah. So the Archidichu takes always from 45 to 9. That's correct.
Got it. Thank you.
You're welcome.
Hi, sorry for interruption.
Yeah.
I'm Venkatramana from the Energy and Resource Institute. I'm a bit curiously interested about the BCSD technique you applied. What is the reference data you use for the bias correction?
The same data, the same exact data that we use for our methods.
So WRF data.
Yeah, WRF data. Yeah.
Okay, great. And also, I'm a bit curious about the last one, about the precipitation. So you are saying that if you validated with the ensemble approach of the rainfall. I'm talking about the figure D and P.
Yeah.
So my point is, if you take the ensemble, you will miss the extremes. How you take care about that?
You're talking about the ensemble mean, right?
Yes, yes, correct.
Yeah, I'm not talking about the ensemble mean. So the CRPS actually takes into account all the members in the ensemble. The same as the spread actually looks at the variance. We're not using the ensemble mean here. Yeah.
Okay. Thank you. Go ahead, please.
Yeah, you're welcome. Thank you. Yeah. So another thing we looked at, since we're interested in extreme risk and not just general bias and so forth, we looked at the ability of this technique to reduce the errors in the prediction of quantiles of different climate fields. And so here, what I'm showing for the different panels is the mean absolute error over the Western United States for each quantile of different climate fields. So I'm showing results for the summer wet bulb globe temperature, for the winter temperature in the middle, and for the wind speed during the fall season to the right. And so the extremes here would be the ones that are closest to the ends of each panel. So quantiles closer to 0 and quantiles closer to 1. And so what we observe for all of these diagnostics and for other variables that we have in the paper is that our method is typically the one that minimizes the error compared to the baselines that we use. So here the baselines that we used are the same as before, BCSD and star ESDM. These are two statistical downscaling methods that are fairly popular. And so here we've introduced another two baselines. So the first one is interpolation, which is just tells you how well you would do if you just use the coarse climate model. And of course, that's the worst performing situation in all cases. But we've also introduced another baseline here that is fairly typical to use in dynamical downscaling studies, which just comes from the fact that because we don't have an unlimited computational budget, let's say that we have an ensemble of 50 members, we can only downscale with a regional climate model, maybe 5 or 10. And in these studies, typically just use 5 or 10 of these models and then assess the quantiles using them. And so in order to use as a proxy the results from this approach here, we've just halved the ensemble size. So instead of using 8 climate models, we used 4 climate models, but we still use the ground truth data from WRF. And we evaluated the quantiles using the sub-ensembles, and the results are shown in pink. And so what we see here is that our approach is still able to improve upon these results in all cases. And this is particularly true for variables that have a strong model uncertainty. And so, temperature and wet bulb temperature, specific humidity, those typically are going to be affected by the subgrid scale physics of the models. But there are some variables that are not that strongly affected by model physics, and they are mostly driven by internal variability, such as wind. And so for those ones, we would expect sub-ensemble selection, this dynamical downscaling method that I was discussing, to perform really well. And so here, what we observe is that our method is able to essentially match the skill of that approach in these cases, and then just outperform it in other cases. And so we show here that essentially our method is fairly robust at capturing the quantiles of the distribution for the right variables as well, such as the wet bulb globe temperature. Finally, when using AI models for climate and for complex systems more in general, it's usually interesting to actually look at case studies. Just because you want to make sure that some of the assumptions that maybe you have about dynamical models actually follow through in these generative models, and they're not doing things that are weird. And so in order to evaluate this, we wanted to understand whether our method could actually work well at capturing the risk of compound extremes in some specific use case. And so for that, we focused on here on wildfire risk over Southern California. So wildfire risk in Southern California is fairly specifically tied to a phenomenon called the Santa Ana winds, which happen in the fall, which just bring very hot, dry air from the desert into the coastal regions. And the wildfire risk due to this phenomenon is captured by an index called the Santa Ana Wildfire Threat Index. And so what we did in this case study is we looked at the ground truth data set of dynamically downscaled results for all the ensembles, for all the ensemble projections, and we picked the date and the climate model that had the highest risk of wildfire in Southern California. Sorry, in the dynamically downscaled ensemble. So after we picked up the date and the model of this event, we essentially took the input coarse climate model data and just passed it through different downscaling approaches. And so the results here are shown on the slide. So the second column shows the results with R2D2, and the third and fourth columns show results with the two statistical downscaling baselines that I was discussing before. And so what we observe is that R2D2 is able to really capture well the magnitude and the structure of the wildfire risk for this particularly strong event, whereas the statistical downscaling baselines either fail at capturing the spatial structure. So star USDM here in the third column, for instance, overpredicts the risk on the right hand side of the panel, so that's upstream of the mountains that get to the ocean, and also underestimates the risk going into the Catalina Islands off the coast of California. Whereas BCSD, which does, for instance, a much poorer job in this case, and it really severely underestimates the magnitude of the risk here. And this is due to the fact that BCSD is unable to capture correlations between different fields, which are important for the Santa Ana Wildfire Threat Index, because this is a nonlinear function of temperature, wind, and humidity. And so to sum up this first approach, dynamical generative downscaling is a method that enables downscaling large multimodal ensembles and capture the risk of compound extremes, such as wildfire risk, as I showed before. And it does so by first leveraging a regional climate model for model generalization, and then diffusion models for computational efficiency. Now, of course, one limitation for some users will be that this approach still requires us to use regional climate models, which are not immediately available to everyone. And so for these users, we wanted to see whether we could go a step further and just enable accurate downscaling of climate fields using purely generative AI. And so for this approach, we've developed a second method that we've called GenFocal, which is a method that is designed to learn directly from unpaired observations. So it's a situation where we're focused on the situation where we don't have access to any regional climate model for training or inference. We just have climate model data that is at coarse resolution and biased. So you can see in the schematic here, that would be the top right world view. And we want to get to a point where we have high resolution bias corrected data, and we only have access to say historical observations of historical weather, which for this case we're going to take the ERFI reanalysis for this. And so GenFocal, as shown in the schematic, performs this downscaling method in two stages. And so in the first stage, we're going to take the biased coarse resolution simulations from a climate model, and we're going to correct the biases at the coarse scale. So we're going to fix the resolution at the input resolution, but we're just going to correct the biases that we observe in the simulations. And then in a second stage, we're going to perform a super resolution process, which is going to take us to the desired higher resolution in this case. And importantly, in this method, and different from other methods in the literature, is that we actually designed this model to retain realistic correlations across fields, space, but also time, and retain time coherence, which is going to be important for emergent long-lived phenomena such as heat waves and tropical cyclones, as I'll show you later. So we've applied this method to the lens2 ensemble, which is an ensemble of 100 projections from the CESM model. And going a bit deeper into the method for the 2 stages, the first stage, so the distribution debiasing stage at the coarse scale, we've used the rectified flow model that learns to match the lens2 statistics for the last 2 decades of the 20th century to historical ER5 reanalysis. So we learned this distribution matching from historical data, but we also applied into the future. Yep. Any questions? Yep. Okay. And then we, for the super resolution stage of our method, we use a diffusion model, so similar to R2D2, where we map the data from the lens resolution, which in this case was 1.5 degrees, to 25 kilometer resolution, which is essentially enforced by the target data that we're using here, which is ER5. And this second step is performed not globally, but on patches, so that it can fit into memory of accelerators such as GPUs. But you can, of course, do this for all patches in the world to cover the entire Earth, if that would be something that's important for the application. So similar to the first method, we evaluated here whether GenFocal can actually capture correlations between variables in time and space. And so here I'm showing different results of this. So in the first column, I'm showing the tail dependence or correlation between extremes of temperature and humidity over the United States in the first row from ERA5, and I'm showing the results, the errors from GenFocal and from BCSD in the second and third row. And so we see that our method significantly reduces errors at capturing the tail dependence of temperature and humidity extremes. Similarly, we wanted to understand whether we can actually capture temporal correlations and temporal structures. And so for that, we estimated how well we capture the risk of 5-day streaks of extreme caution heat advisories, which are defined. It's a defined category by the Federal Agency for Weather here in the United States. And so what we observe here is as well that GenFocal, because it's able to capture temporal correlations, it outperforms PCSD significantly over most regions of the United States. And similarly, we can look at spatial correlations and spatial structures. So for instance, here we looked at the correlation of the 10-meter wind speed over California and the California coast with respect to the city of San Francisco. And so you can see that the spatial structure of this from ERA5 on the top right, the results from GenFocal, which are quite similar in the right hand side in the middle, and then the results from BCSD, which has a much broader correlation structure that is not that it doesn't really capture the fine scale changes in correlation across space. Something else that we wanted to look at here is whether, because we now have a method that captures temporal structure and time coherence, whether we can actually use this for to downscale tropical cyclones. And so this is a setting that is slightly different from other studies in the literature that just perform downscaling in weather forecast for tropical cyclones. And the difference is the following. In weather forecasting, you usually already have resolutions that allow you to see tropical cyclones. And so examples of these are the first row, first and second column here from 2 studies in the literature, where the models start from a resolution where you can already see these anomalies, and you just essentially increase the resolution, sharpen the field so that you can actually get a better estimate of the risk, and so forth. The issue is that climate models actually have such resolutions that they typically do not resolve tropical cyclones right now. And so that's what I'm showing here on the third column in the slide, where we see on the top the climate model predictions for tropical cyclone tracks during the decade of the 2010s versus the actual tropical cyclone tracks that were observed from reanalysis over that period in the bottom right. And so you can see that essentially the climate model that we use for this study, and most climate models actually just miss completely most tropical cyclones. So we wanted to understand whether our method can actually capture tropical cyclones from the large-scale conditions of the flow. And so it turns out that this is the case. And so we apply GenFocal, our method, to the North Atlantic Ocean basin, and we can see that we capture much better now both the frequency of tropical cyclones and also the intensity distribution of tropical cyclones. So we not only get realistic tracks with realistic frequency, but we also get them with the correct frequency, with correct intensity. Sorry, so we are able to recover not only tropical depressions, but all the way to category 1, 2, and 3 hurricanes, which is important for risk assessment. Of course, since we trained this method just on historical data, we wanted to understand whether this method performs well for future climates. And so this is something that we've also evaluated. For instance, here I'm showing results for the warming that we observe from the method in different cities across the Western United States on the left-hand side of the slide. And so here I'm comparing these. Of course, we don't have observations of the future, but we can compare these results to dynamical downscaling and statistical downscaling and see what the differences are. And so the results for our method are shown in green for different, and what you see the spread are just the spread from the different realizations of the ensemble. And as a reference, I've included results from simulations of WRF, so from the regional climate model at a range of resolutions. And also results from statistical downscaling in blue and red. And so what we can observe here is that our method is able to really capture the regional modulation of climate change in different areas, similar to dynamical downscaling. So you'll see that essentially the trend or pattern between the orange and green lines is fairly similar. Whereas, as I was discussing at the beginning of the presentation, statistical downscaling typically just preserves trends in the input climate model. And so this ends up resulting in a much flatter warming or a much more homogeneous warming across cities, as you can see from the blue and the red. So we can see that this method, this generative method, doesn't make that stationarity assumption. And in fact, it can actually capture some of the changes that happen at the regional scale. We've also looked at whether the model is not just memorizing tropical cyclones, but can actually capture or modulate tropical cyclones based on the changes in large-scale conditions from the input climate model. And so one example of that we looked at here was, for instance, how the location of the peak intensity of tropical cyclones changes with climate change. And so what we observe here is on the bottom right of the slide is a weakening in the tropics of the intensity of tropical cyclones and a subtropical widening or strengthening of tropical cyclones, in particular over the east coast of the US. And this is largely consistent with some studies that have shown that there's a poleward shift of tropical cyclones with climate change, due to also the expansion of the tropics in future climates. And so, to sum up here, I've discussed two approaches to accelerate downscaling Earth system models with AI. The first one uses regional climate model projections as training data, as we discussed with one of the questions earlier on. The second one just uses historical data. In our case, we use historical reanalysis to learn the mapping to high resolution projections. Inference as well requires to have a regional climate model for the first approach to drive, in our case, to that 45-kilometer resolution that is common to all the projections. Whereas the second one just requires you to use the two generative AI stages that we developed. And finally, because of these differences, they have different applications where they shine brighter. So the first approach, which leverages RCMs for generalization, can be readily used to downscale multi-model ensembles. So to downscale climate models that have never been seen by the AI model. Whereas the second one is particularly designed for downscaling single model ensembles. And this comes from the fact that the first stage, the debiasing stage, is just learning biases that are very, very specific to the input climate model. And so if we wanted to use GenFocal let's say to downscale multimodal climate projections, we would have to retrain the first stage. And so that's something that has to be weighed in when using these different methods. And so with that, I'll end here. I hope I've convinced you that that generative AI is an exciting technology that can enable translating climate projections to actionable climate information at fine scales. That by capturing correlations, spectra, and extremes, these generative methods can maximize downstream value for users, similar to dynamical downscaling. They don't have the limitations that statistical downscaling methods have. And that through their sampling efficiency compared to dynamical downscaling, they actually enable unprecedented uncertainty quantification compared to the state of the art. And with that, yeah, thank you for your time, and I'll take any remaining questions.
Thank you. Any questions? Yeah.
Hi, thank you so much for your talk. So I had a question about if you wanted to downscale from a resolution to some target resolution for which you don't really have that much ground truth gridded information. So what would be some ways to validate that kind of downscaling? Like, would you have to look at station data and kind of extrapolate how well you're doing from there, or like, are there some other methods?
Yeah, that's a good question, and it's a question that that is going to come up in like many applications. I think there, I mean, so one of the assumptions of this work is that you have a grid at high resolution. And so we've kind of designed the methods for this particular approach. But let's say that you wanted to downscale data to a set of weather stations that are just sparsely located in space. So there, you could use a very, very similar approach. The only thing is that, for instance, when you're designing the machine learning models, there are certain architectures that you are not going to be that useful. And so, for instance, vision transformers or convolutional neural networks are not going to be that useful when you have sparse observations that are not located in a grid. But for these particular applications, you could just, for instance, use a graph-based model. And so you could essentially, in your diffusion model, which is just a model that is trained in a certain way, but has a backbone that can be a convolutional neural network and so forth. If you use a graph neural network there, then you can establish very flexibly the structure of your data. So that's in terms of the spatial distribution of the data. In terms of extrapolation to other points where you don't have much ground truth, I think there's still the issue that you of course want to have enough data to train your model and validate. So there I would probably design the problem in a way where you have enough data at least to validate. So maybe you want to train your data on some other source, but you want to make sure that that you have correct that you have the skill that you need in the locations that you need. So I would reserve a lot of data for the validation procedure in that case, if that makes sense.
Yeah, that makes sense. Thank you.
Hi, Ignacio. Quick question. So when downscaling your data to a target resolution using generative AI, is there any kind of loss that you experience? Is there any data that's lost in this process? And if there is, what's your expected margin of loss?
Could you be a bit more specific about like data? Are you talking about maybe extremes or what kind of data?
Definitely, I'm referring to the extremes because that's what I feel that I think that that's something that probably would be lost in transformation.
Yeah, that's a good question. So we've looked at how well these methods do with extremes, and so for very high percentiles of or quantiles, they tend to do really well. You do have to be careful with like how you train this models. So for instance, like as when you usually start with one of these models and you start with hyperparameter tuning, you might start doing well at the like at the core of the distribution, but you really actually have to train it much better if you want to get the extremes right. So that's one thing that that I would say there, I would consider there. But we typically, we are able, at least compared to the WRF results that we see, or the ERA5 results that we use for the target data, we are actually able to recover fairly well the extremes that are in those validation data sets. That said, we've looked at sort of, extreme quantiles and such that we can estimate robustly. There's been some studies that have come out recently that show skill at what they call record-shattering extremes, which are extremes that were so strong that we were never seeing in the training data. And so for that, I think it remains a bit of a question how well these methods do. So we've seen, I think, from the literature that deterministic models, such as, for instance, GraphCast or Pangu Weather, are going to underperform in these conditions. But I think it remains to be seen whether diffusion models that are really able to retain the sharpness in the features and really sample extremes, whether they underperform. But I think I would always be cautious about essentially understanding whether I'm asking the model too much. So if I want my model to predict well extremes, I want to frame the problem in a way where similar extremes, at least, are seen in the training data. Otherwise, these methods, I would expect to lose some of that information. Yeah.
Right, thank you so much.
Online participants, any questions? Okay, if there aren't, thank you so much, Ignacio, for a very nice lecture. Have a good rest of the day. I think with this, we'll call this today's workshop to an end, and we'll meet early morning tomorrow at 9 a.m.
Thank you. Bye.
So do come at 9 a.m. It's it's a signing ceremony, and 8:30 is for snacks. Yeah, I'm right.